So, welcome again to the new lecture of solar photovoltaics, principles, technologies and materials. So, let us just do a bit of recap. So, in the last lecture we did discussion on silicon solar cell. So, basically we looked at the design considerations, as to what must make a device good. So, we talked about improving the optical coupling of light. So, basically more light should be absorbed into the device. We looked at the strategies to do that. You can do that by texturing, you can do that by minimizing the electrode coverage on the surface, by burying the electrodes into the solar cell, and then you can also put a passive, you can also look at anti-reflection coating on top, which will reduce the reflection. And then we also looked at how to improve the VOC by doping, but doping cannot be indiscriminately large because it also reduces the carrier diffusion length. As a result, your dark current increases. So, there is optimum doping that one can do. And then we also looked at the surface recombination reduction strategies as to how to reduce the surface recombination to make a good solar cell. We will again dwell, we have a few more things to talk about these silicon solar cells before we go to polycrystalline silicon solar cells. So, the next thing in improving the performance in the performance of a solar cell is to reduce the parasitic resistance losses. Okay. And first we will talk about series resistance. Okay. So, basically the idea is to, you can say the idea is to lower the series resistance. This is the important thing, and this is done by basically designing the, this is mostly about the top electrode, okay, top electrode properly. Now, what happens is that if I look at the top of the device, if I look at the top view of the device, top view of the device will have these contacts. So these are the contacts. Okay. So, you have these lines running here, here, here. Now, you want to design these lines in such a manner so that they do not cover top of the surface, but at the same time, so the distance between these lines is extremely important in, so you can say this is D1, D2. So, these contact finger width and spacing requires optimization to minimize the series resistance. If contacts are very far from each other, then again the collection is poor, because you know if you can see that if you have this as a device, and let us say one contact is here, one contact is there, carriers are coming, they are getting collected here, they are getting collected here. But if they are too far, what happens to the carriers which are in between? Okay, they do not get collected efficiently. So, the distance between these contacts is extremely important, and the depth up to which they are buried into silicon is also extremely important. So, one needs to control so what one needs to control is control the spacing. Spacing means both the width and the spacing, but one also needs to control the doping around it. So, the doping around the contact, as I said, that there is a gradient in doping. Okay, it is not a same doping all throughout. So, basically you can say there is a gradient in dopant concentration around the contact. Okay, and generally these contacts are narrow. They are narrow on top, but they are buried which means with high depth. So, they make a good contact by going deep into the N layer, but their spread on the top is low. Okay. So, if you look at the top view, this is low and this is high. Okay. And this is extremely important to improve the charge collection. So, what is important from the perspective of series resistance is to make it go as deep as possible. Of course, you cannot make it very deep because N layer itself is very thin. So, you have to optimize the depth. So, make it go reasonably deep, make it narrow on top and optimize the distance between these two, so that carriers are efficiently collected. There should be no carriers which are not collected. If they are too far, then of course series resistance will increase. They are not, carriers in the middle will not get collected. So, you need to optimize this. So, you need to optimize the width of the contact, you need to optimize the spacing between the contact, and you need to optimize the depth of the contact. These are essential parameters to minimize the series resistance. And if you look at the shunt resistance on the other hand, so if you look at the shunt resistance is mostly a problem. So, basically we want RSH to be high, that is the desirable, okay, whereas RS should be lower. So, this is mostly an issue because of poor material quality or defects in devices. So, you can see that you have a p-n junction here. So, this is p silicon, this is n silicon, sorry, this is n silicon, this is p silicon. If the wafer quality is not very good, if you have excessive amount of defects in the device, the defects or traps will lead to recombination. Defects, traps, etc. will lead to recombination and leakage. So, idea is to maximize RSH by improving process quality, improving the process, which leads to improved material quality. So, basically your leakage current should be smaller, and this is mainly to do with the control of process and material quality instead of design. So, it's less of a concern from the design perspective, but it's more of a concern from the processing and material quality perspective. Okay. And based on these guidelines, there are few kinds of solar cells people have made. So, you can say types of silicon solar cells. There is something called as buried contact solar cell. There is something called as passivated emitter solar cell, something called as rear point contact, so buried contact have efficiencies of the order of 18 to 19%. In this, what happens is that the contact is buried. So, basically the top contact is deeply buried, right. In case of passivated emitter, the emitter is strongly passivated. So, emitter is, that is a top silicon. Okay. So, you have a thin oxide layer on top, which is there in most cases, but so these have efficiencies of the order of about 20% and higher. Rear point contact, sometimes people also use strategies to make the point contact on the back. So on the back the contact is like this. Sorry. So if you have this as a device, so if this is your device, even on the back, so front surface we know is like this, and the contact is buried, and so on and so forth. Okay. In the rear also you can have contact in this fashion. So this is point contact at the rear. So people have done this, they have got efficiencies of the order of 22% or so. Okay. And this lot of work has been done in this area by University of New South Wales in Australia. The Professor Martin Green is one of the pioneers in this silicon solar cell area. So if you go to his web page, and you can also go to website called as pveducation.org, which gives pictures of these solar cells. You can look at them online. And then we have other variations such as passive emitter and rear cell, passive emitter and rear cell. So passivation is done on both front and the back side. So even if this is this solar cell, even the front surface is passivated and the back surface, both are passivated. So both passivated. This again gives you efficiencies of more than 20%, and then we have another one, passive emitter. You can see that common theme is passivation of emitter. Passivation of emitter is very important because the light comes from the top, and N side is thinner. As a result, recombination there is extremely important, surface recombination, and rear locally diffused. This has efficiency of more than 24%. So in this case, the surface is passivated, but on the back side the contact has P plus doping at the base. So as a result, the base is more heavily doped as compared to the rest of the base. So near the contacts there is heavy doping in the P side, and that helps to improve the performance. So these are certain design variations in the solar cells, which are again based on the similar design philosophy that we talked in the beginning. So there are various types of you can see, if you can go online and you can have a look at the pictures of these solar cells. A lot of resources are available, and they will tell you exactly what they look like schematically. So if we just make a summary of silicon solar cells, monosilicon solar cells. So we use single crystal silicon, right? With P type being about N silicon being, which is on the top, about 0.3 micron thick, and P silicon being about 300 micron thick. Okay. So this is called as emitter, and this is called as base. And there is a strong control of doping in such a fashion so that your base resistivity is about 1 ohm centimeter, whereas the top surface, which is emitter, has a sheet resistance of about 100 ohm per square. It is very thin, that is why we talk in terms of sheet resistance. So it is about 100 ohms per square, and it also improves the. It is also important to dope it carefully so that you have good surface recombination, surface characteristics. And then we have surface texturing, improves light absorption, right? Then we have buried contacts with optimum spacing and width, right. This improves the charge collection and lower series resistance. Okay. And then we have surface passivation. We have anti-reflection coating to reduce reflection losses, and this improves lowers surface recombination, you can say. Right. So, these are certain things that we need to consider when we talk about silicon solar cells. So, this is about monosilicon. Now, let us move on to polysilicon solar cells. So, these are, so when we look at polysilicon solar cells, there are distinct differences between the polysilicon and monosilicon solar cell. So, this is taken from Wikipedia. The monosilicon solar cell is very dark. It has absolute dark tinge. It does not have any grains. So, as a result, surface contrast is almost it's a dark surface. If you look at the polysilicon, because you have grains of different orientation on surface, as a result different grains have different reflectivity. There is a surface texture, and you can see this blue, white, black kind of texture on the surface. So, this is on the left. You have two images which show you the texture of a polycrystalline silicon, which is very different to monocrystalline silicon. So, this is a distinct difference between the two solar cells, two wafers from the perspective of distinguishing them. And so, if you come across this, you know that this is a, if you come across a textured surface, you know that it's a polysilicon solar cell. If you come across a very dark looking solar cell, you know it's a monosilicon solar cell. And you can see that you have these contact lines on the top. These are the fingers, and these are again fingers running this way. So, these are sort of the contacts on these solar cells. So, what are the major points about polysilicon? Why do we want to use polysilicon? We use polysilicon because one, easier to manufacture, because of less energy intensive manufacturing. Single crystals are always difficult to make because dislocations are not easy to get rid of. So, you need to do solidification extremely slowly using Shrokalski method or float zone method, which are very slow processes of solidification. As a result, energy cost is very high in monosilicon, and these are low energy intensive processes. Okay. And then the compositional control is less stringent. However, all this does not lead to, despite the above, and of course, they have defects such as grain boundaries. Okay. So, you will have this atomic arrangement like this in one grain. So, this is one grain. In the next grain, you will have atomic arrangement like this. This will be next grain, and another grain may be something like that. So, this is another grain, and then here you may have another grain. So, these are what we call as grain boundaries. So, a grain is a region in which orientation of atoms is similar, and a grain boundary is the one which separates two such regions with different orientations. So, in this case, you can see the atoms are running in this direction, in this case atoms are running in this direction or this direction. There is a misorientation. In this case, the atoms are running in this direction, in this case they are running in this direction. There is a misorientation along same crystallographic direction. Okay. So, let us say if this is UVW this is UVW. The UVWs are at different angles with respect to each other in different grains, and these regions are grain boundaries. So here what is important is the grain size. In polycrystalline silicon solar cells, generally the grain size is of the order of thickness of the device or even larger. So they have larger big grains, they don't have small grains. So grain boundary effect is minimized. So despite our issues, performance is not very bad, is not very poor. So polycrystalline solar cells, as we have seen, they have efficiency of nearly 22 to 23% as of today. So which is comparable, which is not too bad as compared to monocrystalline silicon solar cell, given that you achieve much lower cost. And they require methods to control, require better methods for light absorption or trapping. Okay. Of course, they have grain boundaries, they have defects. As a result, the diffusion lengths are lower. So Ln or Lp are lower as compared to monosilicon. But they have, but you have some good things. They still have, despite our issues, they have good performance. They are more radiation resistant. So this is positive thing, and they are economical. That is the most important thing for any technology to succeed. They are cheaper. There are certain issues that you need to control. So for example, one needs to control. So control of grain size is important. Which means one needs to control the growth of these crystals. Okay, and you need to improve light trapping. Remember, in silicon, monocrystalline silicon, the top surface is all 111 plane, and when you texture it, everything becomes 111. So from 11100 it becomes, sorry, I said 111. So everything is 1100 on top. When you texture it, it becomes, so you have these facets of 111 planes. So in single crystals it's easy. In polycrystalline you have multiple grains of multiple orientations. So you require, so only etching will not work. So you need to do some other things. So chemical etching doesn't work. You may also do some physical methods to improve the light texturing. So texturing of the surface. So surface texturing is tricky, I would say, okay, because you have different orientations. So this is 111, this could be 100, this grain could be 111, this grain could be 110, this grain could be 112, and so on and so forth. Now, to create the same texturing as you created in single crystal silicon is difficult, because chemical texturing works on removal of atoms from certain planes preferentially. So in this case, it might create 111 facet here, but it may not create 111 facet there. It will create 111 facet here, but at different angles. The angles will be different. So surface texturing is tricky. So you need to apply both chemical as well as physical methods of texturing. All right, and you also need methods to passivate the surface. And grain boundaries. Okay. And generally the physical characteristics, so the device is like this. The grain size, so if this is, so this is the grain boundary. The device thickness, so this is device thickness T and this is D. Okay. So, D is the grain size. So, D is generally larger than T, so that you do not have horizontal grain boundaries, you only have vertical grain boundaries. Okay. That is generally the consideration that you have in these devices. Another thing that you often come across is, since you have a grain boundary, the energy grain boundary leads to formation of energy barrier at the grain boundary. So, this is grain boundary. It forms a energy barrier for carriers, and one needs to because it is an internal surface with dangling bonds, as a result the carriers also get trapped. So, it also has traps. So, you need to passivate these traps. So, grain boundary passivation is extremely important here in these solar cells. So, any carrier will find a barrier here at the grain boundary. Okay. So, this is the grain boundary region. So, what do you do in case of these solar cells to improve the performance? So, methods to improve the performance. So, first thing that you do is to use of gettering. Gettering is to use of materials which during the processing which remove extra impurities. Okay. So, use getters, for example, titanium is a good getter because it sucks up oxygen. So, use of this materials which suck up the impurities, so that you have lower impurities, and then you do passivation with hydrogen. Hydrogen is a good passivating agent in silicon. So, use of, for example, SiNX, amorphous SiNXH for passivation of surface and grain boundaries. Then of course, we do surface texturing, as we said, using physical and chemical means, as well as reactive ion etching. Reactive ion etching. And then one can also of course use of anti-reflection coating on top, such as you can have TiO2, Si3N4, etc., which are typically CVD, PECVD, or chemical vapor deposition, plasma enhanced CVD, or LPCVD, that is low pressure CVD processing. So, this is generally about silicon solar cells, polycrystalline and multicrystalline solar cells. In the next lecture, we will talk a bit about the silicon manufacturing, how the silicon is manufactured, and before we move on to the next generation solar cells. Okay. Thank you.